Thank you very much. Thank you. Good afternoon, everyone. I hope you already have enough food. So, my name is San Taile, and I am a research engineer at Nokia Bell Lab. Bell Lab is a very special research and development company with a long and proud tradition of innovation. So literally, all the communication and information-related technologies that you are using today, such as telephony, digital communication, laser, transistor, programming language, were invented at Bell Lab. So at Bell Lab, we asked the question, what could be the human need in the next 5 to 10 years? And we try to develop appropriate technology to satisfy these needs. And today I'm going to discuss with you some key technology in optical communication that we are developing to support faster internet. Okay, so this is a map, simplified map of the global optical communication network, which is the backbone of the internet. This is actually how we are connected globally. And to build this network, more than 3 billion kilometers of optical fiber has been installed, which is enough to connect the sun and the earth 20 times. But we are at a very special, critical point in time because we are facing a very big challenges. So the exponentially growing of even today's services, such as Netflix, YouTube, Amazon, social media, cloud service, and so on, have already put the network to the limit of the today's technology. So the next phase of the information revolution with Internet of Things, mobile HD video, virtual reality, self-driving car, the automation and connection of everything would not be possible anytime soon at a large scale because the infrastructure we have today is not ready for such services. So what are the problems? The first problem is the capacity. So the amount of data that we are generating and transmitting over the network now has been growing exponentially at a tremendous speed of 30 to 40% every year. And if we project the capacity growth over the past 2 decades into the future, we would need to have to support a capacity which is 10 times higher than what we have today by 2025. And this is already a big challenge. And capacity is not the only problem. The future internet would connect people to the services they consume will need to be simultaneously global and local at the same time. So being global is rather obvious because we need to have the access to information and services at any point on Earth. Being local is an emerging requirement because many future applications will require ultra-low latency. For example, virtual reality. Without fast response, we would not have the sense of real-time communication. Self-driving car. A fast response would define the difference between life and death. And the same for remote surgery, manufacturing automation, and other bandwidth-hungry applications. So to build a network which is being global and local at the same time with 10 times capacity is a big challenge, and we need many innovations in terms of network architecture, protocol control, transmission solution, and at the physical layer. And also, we need to keep in mind a very important factor, which is the cost. Because if the solution is too expensive, network and service provider would not be able to adapt to this solution quickly, and we will not move forward. So this is the challenge to solve a big problem at reasonable cost, which it can be beneficial both for consumer and network and service provider. So this is an emerging optical network architecture with the integration of the data center at the edge cloud. So there are 3 network segments, the core and the long-haul network, connecting city, country, and continent, the data center interconnect, and the access network. So for providing the global aspect, the capacity of the long-haul network needs to be increased continuously. And for providing the local aspect, the content and the processing unit should be distributed closer to the end user. In this case, the popular content, for example, can be distributed to many different locations, which provides the capability of the network to provide the service faster at lower latency. And in this case, we have the different requirement here for such network segment in terms of capacity, the cost, and the latency. So what is the challenge of increasing the capacity of long-haul network? So of course, if we need more capacity, we simply can lay out more fiber. However, this is not a very cost-efficient solution because it would cost approximately $300 million to lay out 6 fiber pairs over the Pacific Ocean, providing 10 terabits per second each. So another better option is to increase the capacity per fiber. However, we are hitting a limitation here. So the fiber channel is a nonlinear channel. It means that if you look at the signal at a particular frequency, there is a nonlinear interference from all other channels simultaneously. So if we put more and more channel into the fiber to increase the capacity in the same way like we have been doing in the past 2 decades, the system eventually breaks down. So the fiber nonlinearity here set the upper limit on the amount of power or the number of channels we can put into the optical fiber, and so the activable data rate. So how do we overcome the limitation? This is not a hard limitation, so it can be overcome, but it is a limitation of the today's system. Unfortunately, it's also not an easy problem to solve because nonlinearity in communication system is always a big challenge, a big trouble. So if you don't believe me, you can open a classical textbook on digital communication, which is about 1,000 pages long, and you look for the keywords of nonlinearity. Here is all what you can find. So nonlinear distortion in telephone channel arises from nonlinearity in amplifier and compounder used in telephone system. This type of distortion is usually small and very difficult to correct. The single whole paragraph. No more analysis, no more method of compensation, so we don't know too much about nonlinearity. Unfortunately, optical fiber communication is all about nonlinearity because the fiber channel itself is nonlinear. Because we don't know too much about it, after 10 years of active research, we still don't really have any effective technique to overcome the fiber nonlinearity limitation. And recently, we have found such a technique to beat the fiber nonlinearity limit with the concept of what we call nonlinear Fourier transform. So basically, the nonlinearity in the optical fiber is very complicated and annoying, but it can be predicted. And to predict the nonlinear distortion, we developed a tool called nonlinear Fourier transform. So basically, it's a nonlinear transformation which decomposes the signal into the set of nonlinear mode or nonlinear signal spectrum, which propagate over the fiber channel without any interaction. So without any nonlinear distortion. So if we look at the propagation of the signal in the nonlinear spectrum domain, it's a linear propagation. There's no nonlinear crosstalk. This amazing property suggests that we should encode and transmitting information in the nonlinear spectrum domain. And this is exactly the way we can overcome the nonlinearity limit in fiber optical communication. So here's one example comparison of the conventional system, the performance in the blue curve, and the system we design in the red curve. So by modifying the way we transmit and encoding information, we can move the blue curve to the red curve and achieve a much higher signal quality and achieve much higher capacity. So when fully developed, we expect that the technology can increase the capacity of the single fiber by 50%. To achieve around 36 terabits per second, which is enough to transmit simultaneously 9,000 DVD every second. So let's move to the challenge that we are facing in terms of short-reach transmission. So here the capacity is no longer the priority. Instead, it is the cost. It is the cost, size, and power consumption because of the optical transceiver, because we need a huge amount, 100,000 of them to connect data center. And we need to have a cost-efficient solution. So there are 4 physical dimensions of the fiber channel that we can use for encode and transmit information, namely amplitude, frequency, phase, and polarization. But for low-cost transmission system, can use only one dimension, which is the amplitude or the intensity of light. And the signal is detected using only single photodiode. However, because of the simplicity, we have another limitation here, which is the interplay of the dispersion of the fiber channel, which is frequency dependent of the group velocity of light, and the nonlinearity of photodiode. And this interaction is very complicated, and it's not easy to even achieve 100 gigabit per second over around 80 kilometers, which is the target distance for connecting data center. So in order to overcome this, we need to somehow cancel the interplay of the dispersion and nonlinearity. And we developed such a technique using something called chromachronic processing. So in this transmission scheme, we modulate simultaneously the amplitude and the phase of light. It's a two-dimensional modulation, and at the receiver side, the signal is detected using a single photodiode. So we detect only the intensity because we want to keep the system simple, and then we reconstruct the phase using chromachronic signal processing. So there's some condition for that reconstruction technique to be perfect, but we have shown that with a clever design, we can meet all of that requirement, and the phase can be reconstructed perfectly by detecting only the amplitude. And by doing so, we can massively increase the achievable data rate of conventional system with a single photodiode, and achieving more than 200 gigabit per second using just a single photodiode. And we did some calculation about the cost reduction. It depends on the distance we look at, but we have achieved at least 6 times reduction in the cost per bit if we look at the typical transmission distance of 80 kilometers. So we expect this technique can help the data center can be scaled in a much more cost-effective manner. So in general, with the technologies that we are developing, we believe that the optical communication network can be scaled faster and in a cost-effective manner to keep up with the capacity demand of the internet. So for short-reach communication system, we can apply chromachronic scheme, which dramatically reduce the cost per bit. And for long-haul transmission, we can use a nonlinear Fourier transform, which increase the capacity with no modification of the hardware. So we can achieve 20, 30, up to 50% higher capacity without any modification of the hardware. So in this case, we have different technology options for different network segments to satisfy the capacity need. So in conclusion, according to President Barack Obama, the internet should be always fast, accessible from anywhere, and affordable. And we are working our best to keep it always that way. Thank you very much for your attention.